All right, so page 593, number 14. Number 14 actually follows number 13, which we did the other day. So 13 was what was the difference between the energies of the E4 and E1 energy level of the hydrogen atom. And we found it to be 12.75. Okay, so, and it was a negative because we were assuming it was being emitted. 12.75 electron volts where this was emitted. That becomes important in number 14 because 14 says, by what amount does the mass of a hydrogen atom decrease when its electron makes a down transition from E4 to E1 in an excited hydrogen atom? Okay, so this electron is going to drop down from the 4, n equals 4, 3, 2, to the n equals 1. And when it does that, it emits a photon of energy. That photon has energy of 12.75 electron volts. And it's saying by how much, what's the mass change? Well, I gave you this to see if you could figure out the equation to use because you haven't got to use it yet in your life, even though you know it. The equation that connects mass to energy is Einstein's E equals mc squared. We'll come back to it in nuclear, so they just drop it in here in this chapter without ever mentioning it before. But really what the equation says is how much energy you would get if you took mass and totally converted it to energy. So in this equation, we're giving off this much energy, so it must be that the atom is losing mass. So we can solve for the mass that's being lost by just taking the E we found in number 13 and dividing it by the speed of light squared. So 12.75 electron volts, which of course we have to change to joules. So times 1.602 to the negative 19 joules per electron volt divided by 2.9979 times 10 to the 8th meters per second. And that gets squared. And when you do this, you find out that that hydrogen atom has lost 2.27268 times 10 to the negative 35 kilograms. Now that might not seem like a lot, and it really isn't. Like you think an electron is to the negative 31, so this is even more insignificant than that. But nonetheless, it has lost that much mass when it has emitted a photon. When it absorbs a photon, it would gain that much mass. So it must have absorbed a photon to jump the electron up, and now it's emitting it when it comes back down. So in the end, it's not like it's heavier than it was. It's just getting rid of the mass it had picked up as it absorbed the photon. All right, number 15. From what energy level did an electron fall if it emits a photon of 9.38 times, so we have the energy of a photon to be 9.38 times 10 to the, if I could only see, negative 8? Yeah, negative 8. Oh, that's not the energy, that's the wavelength. Okay, so it has a wavelength, if I had looked at the units. So from what energy level did an electron fall if it emits a photon of 9.38 times 10 to the negative 8 meter wavelength when it reaches the ground state within a hydrogen atom? So energy of a photon is equal to EF minus EI, and the EF is the ground state, so N equals 1. We're going to be able to get the energy of the photon because we have the wavelength of the photon. So what we need to find is the energy that it's of the level that it started at. So first find your frequency of the photon. C equals F lambda. So F equals C divided by lambda. So F equals 2.9979 times 10 to the 8th meters per second divided by 9.38 times 10 to the negative 8 meters. And you should get a frequency of 3.196 times 10 to the 14th hertz. Okay, so now with this, you can find your EP. EP is equal to HF, So 6.626 to the negative 34 joule seconds times 3.196 to the 14th hertz. And you end up with an EP of 2.1177 times 10 to the negative 18 joules. Okay? But if we're going to use it in this equation up here, we're going to need to change it into electron volts. So EP in electron volts divide by 1.602 times 10 to the negative 19, and you end up getting 13.219 electron volts. And it's going to be emitted because it says you end up in the ground state. Okay, so if it's emitted, it's going to have to go in as a negative. So now it ends up in the ground state, E equals 1, negative 13.6 electron volts over n squared. So E1 is just negative 13.6 electron volts. Okay, so now we're looking for EI. So rearrange, EI is going to equal E1 minus EP. So EI is going to equal E1, negative 13.6 electron volts, minus EP, negative 13.219 electron volts. And so E initial is going to end up being negative 0.380859 electron volts. So that's the energy of the level that it fell from, but the question wants to know what was the level. So you go back to Bohr's equation, En equals negative 13.6 electron volts over n squared. And so it becomes n squared is equal to negative 13.6 electron volts over En. So negative 13.6 electron volts over negative 0.380859 electron volts, and you will get an n squared of something like 35.7087. Take the square root, and n is roughly 6. Roughly because the textbook I think doesn't use, I think it uses 6.63, so that's why with the textbook's numbers it didn't work out to be 36 right on the nose. Okay, so that is number 15. Number 16. Now, number 16 has a couple little weird parts in it, so don't stress. I would not do this to you on a test. For a hydrogen atom in the n equals 3 Bohr orbital, find the radius. Okay, so part A. R3 is equal to h squared over 4 pi, KQ squared m, I don't remember the order I gave it to you in, equal times n squared. So 6.626 to the negative 34 joules seconds squared over 4 pi times 8.988 times 10 to the 9th Newton meter squared per coulomb squared, 1.602 to the negative 19 coulombs squared, and then times 9.109 to the negative 31 kilograms. And that all gets multiplied. It was n equals 3 by 3 squared. So R3 ends up equaling something in the ballpark of 7635 times 10 to the negative 10 meters. Just checking to see if I saw that correctly. All right, that's A. B says the electrical force acting on the electron. So this goes back, and this is the part I said I wouldn't do to you. It goes back to this electrostatic force that I showed you way back at the beginning of the year, the KQQ over R squared. So K is 8.988 times 10 to the 9th Newton meters squared per coulomb squared. Q, the charge of an electron, 1.602 to the negative 19 coulombs, The other Q is the charge of the nucleus, which in a hydrogen atom is just one proton. So